freezes, the mobility of the ions goes down, so you're not able to conduct currents as well. In terms of rocks, you see we have these igneous rocks right here, and up into there. Other than the massive sulfides, which are igneous, these tend to be very resistive. We'll get into the fundamental reason for this in a moment, but basically it's the lack of pore space that doesn't allow fluid to exist that causes the resistivities to be high. In terms of sediments and glacial sediments, clays tend to be more electrically conductive or less resistive due to the surface conducting mechanism that we'll talk about in a moment. And then in terms of sedimentary rocks, which in many cases is the type of situation we're measuring in, shales tend to be lower resistivity. Sandstones can have a wide range of resistivities, as can conglomerates. And then as you get to dolomites and limestones, those tend to have higher resistivity just because, once again, you're reducing the pore space. Okay, any questions at this point? All right. So let's talk about something called Archie's Law. There was a guy named Adel Archie. He worked in the oil industry back in the 40s. And he had been working with something known as resistivity logging, where you stick a resistivity measuring device down a borehole or oil well. And he had noticed that there was a certain empirical relationship that existed. When what he really found was that the resistivity of the rock, the bulk rock resistivity that he measured, was equal to or proportional to the resistivity of the water filling the pore space over, or it was directly proportional to the resistivity of the water and inversely proportional to the porosity of the rock to a power right here. So this, this is porosity raised to the minus m, so this is inversely proportional to the porosity. And there was some sort of kind of fudge factor out in front of here. So in this case, this is called the cementation factor, and it's basically related to how well cemented the rock is. The better the cemented the rock is, generally, the less paths there are for ions to flow in the rock, and so that will increase the resistivity. Okay? In general, cementation factors range from 1.3 for poorly cemented rocks that are unconsolidated to 2.2, but this can be as low as, I've seen values as low as 0.6 in near surface, totally unconsolidated rocks, and as high as 2.5 for really, really well cemented rocks. One last thing, phi here is what's called the fractional porosity, which is just the volume of the liquid when it's fully saturated over the volume of the rock, or the volume of the pore space over the total volume of the rock. Okay. Now, that's for a fully saturated rock. One of the things you can do is you can rearrange that expression in terms of what's called a formation factor, which is simply the bulk rock resistivity over the fluid resistivity. So the formation factor then is directly related to only the properties of the rock. It doesn't have the properties of the fluid in there anymore. And it's just given by this value right here. And you'll see, especially in some of the what's known as well logging literature, a lot of things talk about, a lot of papers or a lot of things will be developed in terms of the rock formation factors rather than the rock resistivities, because this allows the description of the resistivity in a way that's independent of the fluid resistivity filling the pore space. Now, if the rock's only partially saturated, then you've got an additional term that goes out front here called the saturation term, where this is the volumetric saturation. So in this case, fully saturated would have a value of 1. If the rock is only half saturated, or the pore space is only half saturated, it would be 0.5. And this is called the saturation coefficient, which once again has a value somewhere between 1.5 and 2.5. So for any given rock, you see there's all these different constants that have to be empirically measured. And you can see ranges in general. You can look at a book and it'll give you a range for different types of rocks. For instance, well-cemented sandstones, or specific types of rocks like the Brea sandstone, which is a famous rock that's had lots of measurements made on it. But they're very empirical. There's nothing in the science that
you can actually go out and predict what a coefficient is going to be just by looking at the rock itself. Now, these all look like pretty simple expressions, but when you throw clays in the mix, things get a little bit more complicated. That's because clays have a net negative charge along their face. So if you have a clay particle right here, the chemistry of a clay is such that you will generate basically a negative charge along that interface right there. So you've got clay over here, and then you got a fluid right here. And what that negative charge does is those anions start to attract cations. And what you end up with is a little cloud of positive ions in the vicinity of the clay, which remain even as you start to dry the rock out. Because as it turns out, these clays have a high capillary tension, and so they will attract moisture to the surface. And so you'll always have this kind of positive charge cloud sitting right on or right next to the surface. And what happens then is when you apply an electric field or a current to a rock containing a clay, that additional charge cloud will enhance the electrical conductivity, that is the ability to conduct a current, and decrease the resistivity in a way that's not predicted just by Argy's equation itself. And so there's been a number of people that have looked at this. The most famous early work that was done was by a duo named Waxman and Smits, and they found basically you could represent the conductivity, not the resistivity, but the conductivity of a clay-bearing rock by two terms. One would be the normal term, and if you look at that, that's just basically the inverse of Archie's expression that we were just looking at. So you've got a normal Archie's term right here, but then there's a second term that's very dependent on chemistry of the clay and the chemistry of the fluid. And you can see that right here. This Q right here is called the cation exchange capacity. So it's how tightly bound these cations are to this clay particle. And you see that the main thing to point out here is you see that things get more complicated as you add clays, in a non-linear way. So we don't really, once things are considered dirty, like a sandstone is considered dirty because it has clay in it, we aren't able to really use Archie's expression as well anymore, because this thing will kind of muck up the calculation. But the main point here for this class is just to recognize that clay will reduce the resistivity of the rock due to this cloud of cations that get introduced in the vicinity of the clay particle. One last thing to mention is, this doesn't just hold for clays. Shales, which are a more consolidated form of a clay basically, also exhibit this property where they have, because shales are basically made of clay particles, okay? And therefore, if you go into an oil field or somewhere where you have well-cemented rocks that contain shales, you will find that the shales tend to be the low resistivity units of the system. In many cases, even if you have a good porous sandstone, the shales will be less resistant than the sandstones, just due to the fact that they have these cation clouds being formed, because it's basically formed from pure clay with imperfection. Okay, so let's real quick just talk about rock texture versus resistivity. There's a number of natural processes that occur that can change the resistivity of what was once a very, very solid rock. For instance, if you have, let's just go through these top ones right here. A well-sorted sandstone will tend to have a lower resistivity than a poorly sorted sandstone. Why is that? That's because basically the well-sorted sandstone will have a porosity of, say, 20 to 30% due to the fact that the grain size is pretty uniform,
Whereas a unsorted sandstone or sandstone with deposition, you've got not as much pore space because you've got finer particles filling the larger, the pore space generated by the larger particles. And so this will tend to have less porosity than this, and so this will have a higher resistivity often than a well-sorted sandstone. Of course, the exception to that is if the pore space in between the larger grains is filled with clays or silt particles, then this might have a lower resistivity than this just because of the effects of the clays. Limestones, it's really hit or miss. Depends on how much dissolution has occurred in the limestone to create porosity space or how much fracturing has occurred. Limestones are often considered to be highly resistant because they have low pore space, but in many cases you might get quite a bit of dissolution, for instance in karst terrains, where then you have a large amount of pore space, very open throats for the ions and the current to travel through, and so in those cases you will have a lower resistivity limestone. Granites, really, your porosity in granites really comes from fracturing or weathering. So in general, granites or most igneous rocks will tend to have very high resistivities unless they've been significantly fractured or a lot of weathering has occurred. And then basalt, it can often be, and other extrusives can often be actually rather low resistivity simply because when they come to the surface and start flowing, you have gas escaping to create these bugs, and you might have, as they cool, fracturing